let's look at a few examples of calculating surface areas of rotation using these surface area integrals. So let's start out with this one. We're going to find the surface area swept out by the graph of 9x equals y squared plus 18 for y values from 0 to 6, and we're going to rotate this graph about the y-axis. So just to get a handle on this, let's draw a picture of what this situation is. Given the fact that our bounds are sort of given in terms of y, and this equation, it's almost almost x as a function of y, it seems like we should use y as our independent variable. So let's solve this equation for x. We get x equals 1 over 9 y squared plus 2. And this is a parabola. It's a parabola that opens in the positive x direction. So something like this. Right, it's been shifted 2 in the x direction because of that plus 2 there. And we have the part of this parabola that goes from y equals 0 to y equals 6. So that's something like this. And we're going to rotate this about the x-axis. And when we do that, we get sort of this parabolic bowl shape. So we're going to be finding the surface area of the sides of this bowl, not the circular piece in the end. Remember, surface area integrals only add up the surface area that's covered by the graph as the graph rotates around the axis. Okay, so the area that we're going to get is, in general, to find one of these surface areas of rotation, we're going to integrate 2 pi r ds. And all we need to do is figure out, in this situation, what is the radius of the circle that a piece of arc length moves around, and then we need to express ds, that infinitely small bit of arc length, in terms of the independent variable that we've chosen. So again, the independent variable that we chose was y, and the axis that we're rotating about is x. Okay, so our independent variable is y, so right, here is a typical little piece of arc length. It's going to go around a circle like this, and the radius of that circle is this green distance here, and that green distance is just y. So for our integral, r is actually just y. ds, we need to write ds in terms of our independent variable, which is y in this case. And ds in terms of y is the square root of 1 plus dx dy squared dy. So we're going to need to know dx dy, so let's calculate that. Dx dy, right? We're just going to take the derivative of this up here. So dx dy is 2 over 9 times y. All right, so now we can put ds into our integral. It's the square root of 1 plus 2 over 9y squared dy. All right, and of course our bounds are y values from 0 to 6. All right, now we have an integral that we can evaluate. So let's simplify this, I guess. So integral from 0 to 6 of 2 pi times y times the square root of 1 plus 4 over 81 y squared dy. All right. For this situation, it looks like, because we have a squared inside and a y outside, it seems like a u substitution will do the job. So let's let u be 1 plus 4 over 81 y squared. Then du is 8 over 81 times y dy. Let's get these constants out of the way. So 81 over 8 du is equal to y dy. Right? Right? And we have a y to play with, and we have a dy. So this is going to work out. Let's take this 2 pi and move it outside the integral. So 2 pi integral, let's see, when y is 0, u is 1. And when y is 6, let's see, y squared is 36 times 4. Let's see, that's going to be 120 plus 24, so 144. Okay, so 1 plus, so that's 144 over 81, plus 1 is, so plus another 81, so, okay, 225. 225 over 81. That's quite a messy number. So y is going to go together with dy to make 81 over 8 du. And then this square root just turns into the square root of u. All right. So let's see. I guess we can cancel this 2 with part of this 8, so that leaves a 4 down there. So 81 over 4. And then when we integrate, we get a 2/3 u to the 3/2. And this is going to go from 1 to 225 over 81. Okay, so we can simplify some constants here. This leaves a 2 behind in the denominator, and that 2's gone, and then this 3's gone, and this 81 turns into a 27. All right, so we get 27 over 2 times a real mess, 225 over 81 to the 3/2 minus 1 to the 3/2, which is 1. Okay. And, you know, we actually could simplify this. 81 is a perfect square. 225 has a perfect square as a factor. So we could simplify this, but I think you get the point. So we'll stop here. As usual, if you wanted a decimal approximation, you could just dump this whole mess into a calculator. All right, let's look at another example. So let's express the surface area of a sphere with radius capital R as an integral. So you might know a surface area formula for a sphere, but we're actually going to see if we can write down a formula that, or an integral that might produce that area formula. So if we have, so here's a sphere, right? And a sphere is a surface of rotation. So if we can generate a sphere by starting with a semicircle and then rotating it around an axis like that. In fact, we could rotate this around, well, let's do it this way, yeah. So we're going to take this semicircle function and rotate it around the x-axis. So we're going to need to write what this semicircle function is. Well, this is a circle of radius r. So the circle is x squared plus y squared equals r squared. And if we want to write this as a function of x, then we should solve for y. So y is the square root of r squared minus x squared. And here I'm taking the positive square root here because we're dealing with the top semicircle and not the bottom semicircle. Okay, for our bounds, we're going to go from the left part to the right part, but that's from negative r to positive r. So while we're at it, before we get started, let's calculate this derivative, dy dx, because we're going to need it when we write down ds. So it's, let's see, we're going to have to use the chain rule when we calculate this derivative. So 1 over 2 square root r squared minus x squared. And then the chain rule says we have to multiply by the derivative of the stuff inside the square root, which is minus 2x. So that 2 cancels that 2. So we get x over square root r squared minus x squared. All right. So the area is the integral from minus r to capital R, or sorry, minus r to plus r, 2 times pi times the radius, and right, when we have a bit of arc length here, it's going around this way, and so the radius is y, and y is right here in terms of x. So our radius is the square root of capital R squared minus x squared times ds, which is the square root of 1 plus, and then we're going to square dy dx, so x over square root, sorry, I'm missing a minus sign here, so this should be minus x over square root of r squared minus x squared dx. All right, so we've expressed this area as an integral. Now this integral looks like a real mess, but let's see if we can make any progress on it, just to see if we can produce the sort of classical area formula for a sphere. So integral from minus r to capital R, I guess we might as well move this 2 pi to the outside. Here we have a product of two square roots, so we can put these two square roots together, right? The product of two square roots is the square root of the product of the insides. So that we can write this as the square root of r squared minus x squared times 1 plus this stuff squared. I'll multiply out this squaring. It's x squared over r squared minus x squared. Okay, this actually is looking a little better because if we distribute inside the square root, we're going to get some nice things happening. So this is 2 pi times the integral from minus r to plus r. Inside the square root we get, so r squared minus x squared times 1 is r squared minus x squared. And then r squared minus x squared, when we distribute to the second piece, it cancels with the denominator and we just get plus x squared. Okay, dx. And so these x's cancel. So 2 pi times the integral from minus r to plus r, square root of r squared dx. So 2 pi, this is just r, but right, it doesn't have an x in it, so it's a constant. We can move it outside the integral, so that's a factor of capital R. Integral from minus r to plus r dx. But the integral from minus r to plus r is 2r. So you can work out the details if you want, but it is 2r. So this is 4 pi r squared. And what do you know? That is the classical formula for the surface area of a sphere. So that's pretty slick. If you had any doubts about the surface area of a sphere before, hopefully now you trust this formula because we just justified it with an integral. All right, let's look at one more example of a surface area using an integral. So let's express this area as an integral. So we're going to take y equals x cubed from x equals 0 to 2, and we're going to rotate about the y-axis. So let's see, that's going to look like, so from 0 to 2, y equals x cubed looks like this. We're going to rotate about the y-axis. So we're going to get one of these cup shapes again. So this is y equals x cubed. We know we're going to need the derivative here, so let's take the derivative of y with respect to x. So that's 3x squared. So the area is, right, in general, it's the integral of 2 pi times the radius times ds. So in this situation, when we have, so we're going to be using x as our independent variable. So in this situation, right, here's x, here's a bit of arc length. This bit of arc length goes this way as we rotate around the y-axis. And so the radius of that circle that the arc length is going around is x. So our radius is just x. And then ds is the square root of 1 plus, in here we're going to put dy dx, which is 3x squared. Square that, dx. And our bounds are from 0 to 2, of course, because that's right here. Okay, so simplifying this integrand, we get integral from 0 to 2 of, let's see, 2 pi x times the square root of 1 plus, looks like 9x to the 4th dx. Okay, so can we go any further with this? Well, it's a little hard to know what to do. It's tempting to try to break up the integral using the fact that there's a product here, but remember there is no integral product rule, at least not that we've seen yet, so we can't do that. I think the only trick that seems plausible is taking this inside piece and using that for a u substitution. So let's see what happens if we do that. We get u is 1 plus 9x to the 4th. Then du is 36x cubed dx. But that isn't looking too promising because, right, we'd like to see an x cubed outside of the square root, but we don't have x cubed, just x. So that doesn't look so good. Since we just have x here, you know, du, maybe du should just have x in it, in which case u should just be x squared. So maybe we should try u equals x squared, then du would be 2x dx. So this looks a little more promising. Move that 2 over, so 1/2 du equals x dx. All right, now we can do a substitution. I'll do it over here. Let's move that 2 pi outside. Integral, while we're at it, let's translate these bounds. When x is 0, u is 0. When x is 2, u is 4, right, because we're squaring here. So this x, together with dx, make 1/2 du. And then inside the square root, we have the square root of 1 plus 9 u squared. Right? X to the 4th is x squared squared, and so that's u squared. So what now? Well, I mean, we can simplify the 2 and the 1/2, sure. But at this point, it's hard to know where to go. Right? Hard to know where to go from here.